Dear friends and colleagues, welcome to our next seminar of the PhD program in Aerospace Engineering. I would like to welcome Esteban Ferrer. Thank you for being here today. It's our pleasure. He's going to be talking about new avenues in high-order fluid dynamics. And Esteban is a professor of applied mathematics at the School of Aeronautics here in Madrid, UPM, where many of us studied the bachelor and master. He did his PhD in Oxford, University of Oxford, and has 20 years of industrial and academic experience in developing numerical techniques for fluid mechanics problems. He works actively with industry and coordinates 2 European Union projects. And his main interests include high-order methods for fluid dynamics, turbulence modeling, machine learning, and aeroacoustics for aeronautics and wind energy. He has written more than 90 journal and conference papers on all these topics. And hot news today is that Esteban, just 2 days ago, was granted a ERC consolidator grant called Off-Caustics. So congratulations for that. I'm sure you're going to be doing great work, and I'm sure he's going to be talking about it a little bit in his talk. So Esteban, please, the floor is yours.
So thank you very much. Thank you very much for the invitation. So I will start directly. Today I'm going to be talking about new avenues in high-order fluid dynamics. So this is CFD coding. And then I will thank my collaborators in industry and in academia. And I'll start directly. So I also have to thank my students during the past years and some of the funding, mainly European funding. Right, so in the department, in our group, what we do is mainly develop high-order numerical methods. So these are based on discontinuous Galerkin, and you don't need to know what that is. I'm going to explain what that is. We do that for incompressible and compressible flows. And we also use these high-order methods to do flow control. So we work on stability sensitivity analysis to know where we have to touch the flow field to make it more stable. I'm not going to be talking about this today, but that can be a talk for another day. We apply these methods, all this machinery, to aeronautical applications, wind tidal turbines, and multi-phase flows, and I will give you a glimpse of the things we are doing these days. So briefly, my talk is a brief introduction of high-order methods, and in particular discontinuous Galerkin. This is to give an overview. Then I will be talking about the new features we're adding to our solvers. So in particular, moving meshes, moving geometries, multi-phase, and turbulence. And then finally, briefly on acceleration techniques, so new ideas that we are developing, some of them based on neural networks, machine learning, etc. Right, so I'll start with the introduction. So for those not familiar with high-order methods, the idea is simple. So in low-order methods, we typically have a mesh made of triangles in this case, and we have a piecewise linear, piecewise constant function inside each element to represent the solution. We can also use piecewise linear representations inside each of the triangles, and that will be something similar to finite elements. Now, in higher-order methods, we use any polynomial order to represent the solution in each of these triangles, right? So here I'm plotting polynomial order 2, polynomial order 3. And we can go to an arbitrary order. The idea then is that by using a higher order polynomial, I can capture better the solution inside each of these triangles. Of course, we can do 2 things, right? We can increase the number of triangles if we want a better solution. I add more triangles. This is the classic H refinement technique, also for low order methods. Or I can fix the mesh, I can fix the number of triangles and increase the polynomial order, right? And one will think, why would you do one or the other? And the answer is, I'll try to explain in the next slide. So increasing the number of triangles, we call H refinement. Increasing the polynomial, we call it P refinement for polynomial. Right, so in fact, what we're doing is kind of increasing the number of points that we have inside each triangle, right? So we need certain points to fit a polynomial, right? And then what we are effectively doing, so if you see a higher order mesh, what you see is very coarse mesh, something like this, very, very large elements, and you think, okay, this is very badly resolved, this is pretty crap mesh, but in fact, because you're using a higher order polynomial inside, you could represent every inner point in the thing those are the effective degrees of freedom that you're using. That means that, well, this is kind of what we see. So what would you do, one or the other? So this can be seen in this easy plot. We have a Poisson equation. This is an elliptic equation. I'll show you more complex cases later. And here we have the error norm. So this is we know the exact solution. We can compute the error between our numerical solution and the exact solution. And here we are plotting the degrees of freedom that we use to solve the system. So this is the size of the matrix that we need to invert to get the solution. Now, here there are different things here. So we have 4 different meshes, from 32 triangles to 128 triangles, different colors, right? So these are these different colors. And then in the boxes, we have the polynomial that we are using to solve the system. So if we fix, for example, the polynomial to a low order polynomial order 2, what we see is that, and the only way then is to decrease the error by increasing the number of triangles, we see that the error decreases following this line. This is what we call edge refinement, increasing the triangles, fixing the polynomial. Now, if we do the reverse, we fix the number of triangles to 32, the very coarse mesh, and we increase the polynomial order 2, 3, 4, 6, 5, we see that the error decreases much, much faster. So, in fact, what this means is that if we require a particular level of accuracy, let's say 10 to the minus 7, we want this level of accuracy. If we use a coarse mesh with a high polynomial order of 6, we will need this number of degrees of freedom. So this is the size of the matrix that I need to invert. However, if I use a low order method, for example, polynomial order 2, I have to go way outside the board to get the number of degrees of freedom that I need. So this is many more degrees of freedom if I use a low order polynomial. That means a larger matrix that I have to invert, means a more expensive calculation, in fact. Right? So this is the potential of higher order method. Fewer degrees of freedom to solve with the same accuracy with a low order method. Now, of course, you will say this is a very academic problem, this is an elliptic problem, that's very easy, blah, blah, blah. Okay, let's see a more realistic thing. So if we compare, for example, a fluent computation. This is a commercial code, low order method, right? Second order in this case, with this fine mesh here. What we see is that very quickly the vortex shed from the airfoil are quickly dissipated by the numerical errors in the solution, right? And this has nothing to do with turbulence. This is a laminar flow. So this is pure numerics. However, in the higher the setting, so this is a very coarse mesh, but with a polynomial of order 5, what we see is that the structures are very well captured for a long time, and this is because of the numerical errors being much, much smaller than in classic commercial codes. And we see this kind of behavior over and over in all our computations. So this is another example. For example, we're comparing a DNS for an airfoil. We compare that to, again, a fluent, low order, and with a URANS, for example. And we see that more or less we capture the structure of the separated region, but we're missing all the Kelvin-Helmholtz instabilities in the shell layer. If we go to a higher order setting with a polynomial order 5 with a terribly coarse mesh, so this is made in purpose very coarse, what we see is that we do capture some of the structures, some of the Kelvin-Helmholtz instabilities, not all of them, of course, because the mesh is purposely very coarse, but we start capturing much more rich flow than in the case of low order methods with URANS. Again, we can compare fluent against LES for a rotating airfoil in this case, and we see again a very smooth flow in fluent, missing all the frequencies, and however in the higher the setting we have a much more rich flow. If we look at the comparison of the numerics with the experiments, we see that the high order method captures pretty well the forces, right? However, the fluent setting, because of this dumping all the frequencies, dumping everything, misses actually the forces. Right, so this is a motivation of using higher order methods. We have higher order methods pretty well developed for laminar, turbulent flows, moving geometries, etc. And I will show you now some of the things that we are doing these days. Right, so currently we are developing a solver that is called Horses, and it's freely available on GitHub. You have it here. And we are now finishing the review of this paper, which is available in an archive, where we show some of the features that we'll show you today. So some of the examples of the new things we are incorporating into the solver. So I'm not going to go into the basic mathematics, I'm just going to show you the new things we are In particular, we have all this stuff here, LES, runs, and a bunch of different things. I will show you some today. Right, so this is a slide representing more or less the things that I'm going to show you today. So mesh-free methods, multi-phase, runs, LES, some acoustics, a little bit, all this stuff. Right, before going into that, I'll show you some of the scaling of our higher order solver, right? So the nice thing about our solver is that we can change the polynomial order, and this is done you don't need to recompile the solver, it's just a parameter in your input file. You change the polynomial and then you're running with a higher accuracy, right? So this is the polynomial we were talking before about. Right, and then we can do scaling, and we have here 1,000 cores. We have run that now up to 2,000, and the results are similar. And what we observe is we have combinations of MPI and OpenMP in parallelization. And what we observe is that when we increase the polynomial order, so we're enriching the solution with degrees of freedom, we are approximating the ideal scaling, right? Up to quite a lot of polynomials, a lot of cores, sorry. And that means that it is advantageous to use higher order polynomials, right? Both in terms of accuracy and in terms of parallelization as well. Furthermore, we have tested that even further for more complex problems. So if we look at the acoustics of an airfoil, for example, so this has an LES model in it, so this is a much more complex problem, and we're looking at the acoustics. That's the waves, acoustic waves that emanate from the trailing edge, right? And then propagate up to a certain locations here where we're measuring the noise, and we can plot the sound pressure levels against the frequency for this particular location, right? What we see is that first we check the accuracy, and what we observe is that when we increase the polynomial order, we are getting this spectral convergence, this very rapid convergence that we get for the very basic flows, right? This elliptic problem where everything were decaying very fast. We also observe it here in a much more complex simulation. So we do get this exponential decrease of the error, this very rapid decrease of the error. And however, what's interesting is that if we check the cost in running these simulations, we can see that when we increase the polynomial order, for example, let's see this mesh. So we're fixing the edge mesh. This is all the same number of hexahedrals in this case. And we increase the polynomial order, the cost only increases linearly. So we don't have an exponential increase in cost. The cost is only increasing linearly, whilst the error decreases exponentially, right? So this is the big advantage. If everything was exponential, well, probably wouldn't be advantageous, but this is what makes things very nice. So we have to run high polynomial orders. Right, so that's the basic introduction to higher order methods. Now I'm going to go into the multi-physics and to show you a few of the things we are incorporating. Right, so moving meshes. In the past, so during my PhD basically, I developed this sliding mesh technique where there's an inner mesh that rotates and another mesh that is static. And what we can see is that the interface between both, when you use higher order methods, doesn't introduce any spurious oscillations, any errors, right? So the contours don't even see the interface across where they have to go across, right? So this is a very accurate method, and it can be shown that it works for all polynomials, etc. So it works pretty well. We have to deal with hanging nodes. However, the problem is it's a bit costly, right? We have to deal with these interfaces and hanging nodes, etc. So these days, we have switched a little bit. We haven't abandoned sliding meshes, but we have switched to an easier method, which is a mesh-free method, an immerse boundary method in particular, which hasn't been applied a lot for higher order methods. Right, so we were interested in doing this. And these are very nice because you only need a Cartesian mesh or something that it's almost Cartesian. You don't need to include the geometry. You don't need to do the tedious process of meshing, right? So this you can avoid. And you only include a source term that represents or mimics the effect of the solid body. So the nice thing is we can do complex geometries. We can do moving geometries very easily. And again, there's no meshing. And for those who have done CFD in the past, meshing is horrible. We all hate meshing, and doing no meshing is very nice. So this I'm very excited about not meshing anymore. Right, so if we do moving airfoils, we can do moving airfoils very easily, as I mentioned, and we do get the right physics. We have a few papers on this, a few papers on checking the errors, modifying the formulation to minimize error, etc. But well, it can be done. It's very, very nice. And what we were getting all the time from the reviewers is the criticism that sometimes these methods lose certain accuracy near the boundaries. And if you lose accuracy near the boundaries, you might wonder why use higher the methods if you're losing accuracy near the boundaries. So we went and checked that, and we're still checking that. And what we see is that when we increase the polynomial order, so this polynomial order, we do get this spectral convergence as well in terms of lift and drag. So we are recovering the nice properties of higher order methods, even if maybe locally we are losing some of the accuracy because of the immerse boundaries, right? So this is something we are exploiting now, and we're trying to exploit this higher order methodology with the immerse boundaries. So we can push that further and run, for example, a rotating wind turbine. And again, I should point out that we only need the CAD file, so the STL file. We throw that into Horses, our CFD solver, over a simple Cartesian grid, and we get the points that need to be penalized as time evolves, and basically we get a flow field. So there's no geometry whatsoever, but the flow is filling the geometry, right? In this particular case, we refined the mesh with a high polynomial order of the 3. We left a low polynomial order in the region where there's nothing is happening, and I can always overlay the STL file, but it's not in the flow, but you can always overlay to see if it's physically correct. And then when we see the flow field, we recognize all the features that one will expect on a wind turbine. So you have the tip vortex, you have the leading edge accelerations, you have the tow wake, so you have all the necessary physics to represent wind turbines. And this is something we're exploiting now because no meshing, it's very nice, at least for me. Right, so that's briefly on moving stuff. So of course the blades were moving here, so that's where the moving was. I'll show you some on the multi-phase stuff that we're doing. Right, so this is taken from a paper, from a review paper that is down here, where they summarize all the possible ways of computing multi-phase flows. So in particular, of all these methods, you might recognize the VOF, the volume of fluid. This is very classic, level set. We don't choose any of those. We use phase field models. And I'll tell you why. So phase field models require additional equations to be solved, but they can represent the interface between the two fluids, the air and water, for example, as a smooth function. So this is similar to a hyperbolic tangent, right? So it's a function that can be differentiable, everything, it's nice. And this is very advantageous in terms of higher order methods, because if we have an interface that is very sharp in a higher order setting, you can imagine a Fourier method, you will get Gibbs phenomena. You will get oscillations, you will get instabilities. However, if the interface is smooth, as in this case, then the higher the method is well behaved, you can refine at the interface, everything is nice and smooth. So that requires solving Navier-Stokes equation plus some additional equations, the Canhillier equations, which are not easy to solve, I must mention, because if you plug this guy into this guy, you get a fourth order derivative, so it's not easy to solve, but we can do it. So we have run that for a few classic test cases, such as those ones. And what's very nice, so the method is conservative, it has very nice properties, etc. What we can do now is, since we can afford to throw more degrees of freedom at the interfaces, because we're not going to get oscillations, we can refine only at the interface to better capture the sharpening of the interface and these features that occur at the interface between air and water. And by doing this local increase of the polynomial, we can decrease the computational cost by 50%. So this is the idea on multiphase. We have a few papers on this. And there's a particular feature that I haven't mentioned. Let me just explain very quickly. Okay, those are almost the only equations that I have here, and you don't even have to understand them. Okay, so the key idea to do under-resolved flows is that typically what happens if you run these multi-phase simulations, if everything is well resolved, you have a lot of accuracy at the interface, everything will run smoothly, and you get a converged solution. If you don't, if you have aliasing errors because you don't have enough accuracy, what's going to happen is that it's going to blow up, right? And you're never going to get a stable solution. A solution. So the basic idea of these energy conserving schemes, which is the energy or entropy conserving schemes that we use or we develop, basically for multi-phase we develop it from scratch, is, okay, I have to solve the Navier-Stokes equation, so I'm going to discretize the Navier-Stokes equation. What happens when you discretize the Navier-Stokes equation is that there's no guarantee that the discretized version of the Navier-Stokes equations are going to conserve energy, are going to conserve entropy, are going to conserve additional variables that are not the ones that you are solving for, right? However, the continuous Navier-Stokes equation do fulfill the energy equation, do fulfill entropy equations, right? The continuous level. So what you do is you discretize the Navier-Stokes equations and you make sure that the new equations that are discretized also fulfill the discrete version of the energy equation, the discrete version of the entropy equation. Do you solve additional equations? No, you solve the same equations, but on the paper you check that these discrete equations fulfill these additional constraints. And what you make sure of is that you don't have buildup of energy that makes things explode, you don't have buildup of entropy or something like that, because everything is conserved, because you have made sure that the discrete version conserves all these quantities. So then what happens is that, okay, if we have a very smooth interface, as in this case, the normal solution and the entropy stable solution work perfectly, you get good solutions. However, when you start having sharpening at the interface and you have some lack of resolution, and you start having aliasing errors and building up of energy, if you're not careful, things blow up. But if we use an energy stable discretization, things are okay and you get a final result. And then that gets even more accentuated when you have more sharpening of the interfaces, right? When the normal discretization blows up very quickly and the other one gives you an answer. So there's a lot of advantage of this. Of course, this technique that we use for multi-phase, we also use it for turbulent flows because that's where you have under resolution and also these techniques help. Right, so talking about that, I'm going into turbulence. Okay, so in turbulence flows, you can run simulations, you can run LES simulations, and in our solver, we can do both. Here I'm showing you a run simulation with the Spallat armors for this particular NASA workshop body. And what we observe in this run simulations is that we get the very high accurate solution when we increase the polynomial order. So this is our solution, Horses 3D, from P2 to P6, right? And what we observe is that very rapidly, when we increase the polynomial order, with fewer degrees of freedom, because this is shift to the right, we get the accurate solution, and much faster in terms of degrees of freedom than when we compare to classic low order methods. So for a turbulent flow with runs, also we get this advantage of the higher order method. This is another example for a plane. We run it with our solver, we compare to the Numeka solver, and again, we get very quickly the right solution when we increase the polynomial order as compared with the low order simulation. Right, there's a small detail. When you run runs, you want to have a steady state solution very fast. You want to reach the steady state solution very fast. And hence you have to worry a little bit about the numerics. I'm not going into the details, but here we have a combination of multi-grid together with some semi-implicit smoothers. And what we managed to do is to decrease the wall clock to get the steady state solution by a factor of that was 10 to the 5 with state-of-the-art method. This is local time stepping. Don't need to know what it is. It's just state-of-the-art. And then what we get is 10 to the 3. So we have 2 orders of magnitude less computational time to reach the steady state. Right, so this was runs. People are not so much interested in runs these days, but we work with industry, so they are interested. We also run LES simulations. And what we see, for example, when we combine these ideas of entropy stability that we saw for multi-phase, we combine it for LES, so same ideas, make sure that everything fulfills the discrete version of the energy equation, such that it doesn't blow up. What we see is very good agreement in terms of lift and drag for these airfoils. For example, that's Reynolds 1 million. Right, more things. We are also developing new turbulence models, and the idea is in turbulence model in discontinuous Galerkin, I've talked about the higher the polynomial. I haven't talked about the fact that we call it discontinuous Galerkin, right? So the word discontinuous means we have higher order polynomials in each element, but we allow for gaps between the elements, right? So we allow for discontinuities between the elements, hence the discontinuous Galerkin word. And what we observe is that these gaps are very small if we have a very fine mesh. So if it's well resolved, we don't have gaps. But when we don't capture well the solution, what we get is large gaps, right? This is because the polynomial cannot really fit into the solution, right? So and hence we get these gaps in. So an idea is to link these gaps, what we call jumps in the solution, to the viscosity, to the under resolution in our flow field. So what can we do? We can include a viscosity, an LES model that relates to these jumps, right? So these jumps are telling you how well resolved you are. If you are badly resolved, you include more viscosity. If you are well resolved, you don't include any viscosity. That's the basic idea. You can do that with the solution, the jumps in the solution. You can do that with the jumps in the gradients. Potato, should be similar. And what we see is that when compared to Smagorinsky or Riemann models, these are classic LES models. So this is the Taylor-Green vortex, so I should explain what that is, sorry. So this is an academic test case that we like because it's you start with some blobs in your solution, periodic boundary conditions, and then turbulence starts to develop. We have some transitional flow, and then an isotropic decay of turbulence eventually at the end. So what we see is that when we compare our solution jump, gradient jumps, to the classic Smagorinsky or Riemann models, we get much better solutions. So we have a DNS solution here in black, and we get with this idea of relating the viscosity to the jumps, we get much better solution than with classic explicit LES models where things are based on the physics and not in the numerics. Right, we are also now trying more things in terms of implicit. This is work with the BSc, with Oriol Lemhout in Barcelona, so we are working on this as well. We are also collaborating with McLaren, where we are comparing our solver in the LES setting to this solver here. So this requires quite large meshes, but we're trying to do it, and we're getting roughly the good results, we think. Also, another thing I'm not going to talk about, just this slide, is that we have included the possibility to capture shocks in higher the setting, as you can see here in terms of runs or LES simulations. And that's about it for turbulence. Let me now briefly mention some ideas on the acceleration part. Right, so I don't know, how long do I have? Sorry. 10 more minutes, perhaps? Okay, so one thing that we can do, we talk about using a higher order polynomial in some regions, lower the polynomial in other regions. So, of course, we can increase the polynomial order to get more accuracy, but the idea is to use the higher order polynomial only in the regions that are interesting, right? If you are far away from the action, so this is a boundary layer developing here, for example. Here we have a lower order polynomial. We don't need to do anything. We don't need to capture anything. So let's use a lower order polynomial. However, in the boundary layer, this is a laminar boundary layer, we have a large gradient in this direction and very small gradient in this direction. So let's use a high polynomial order in this direction to capture the growth of the boundary layer, and a low polynomial order in this direction. So we can vary anisotropically the polynomial order that we use in each element. Right. So one thing is how you choose this polynomial order in each direction. So what we can do, so we base one of the ideas is to use truncation error, and I explain it with two equations. It's very easy to understand, so I think I can try. I'll explain for steady state. So in the steady state, we have this is Navier-Stokes equation. In steady state, this term is 0, so we get this guy here, and then the truncation error was defined a while ago the difference between the Navier-Stokes operator at a particular level of accuracy, this is discretization in order n, minus the exact operator, Navier-Stokes operator. And this difference gives us an error, a quantity of the error. This is the exact solution in the continuous framework. This is the discrete framework, right? And this difference gives us the error, an error in our solution. Now, of course, if we are steady state, this guy is 0, and we are left only with this guy. This guy here gives us directly the error, a measure of the error in our mesh. A detail is that here we have to plug the exact solution. And of course, the exact solution, we don't have it. If we had the exact solution, we didn't need numerics, okay? But we need to do something about this U guy here. So what we do is we run a finer mesh to approximate the exact solution at a level P. And by plugging U at a level P into the Navier-Stokes operator in N, what we get is an estimation of our error. Okay? So if we do so, if we run a P solution, this point here, this is the P solution, we run this guy here. Then we extract the solution that we got and we plug it into cursor operators, right? So the cursor operators, we don't need to rerun all the simulations in cursor mode. What we do is only plug the solution into this and it gives us a number, right? And these numbers are all these dots here. Now we know that this error behaves as we saw initially. It decreases very fast with the polynomial error. It has this spectral convergence thing. So we can fit an exponential curve here. This is an exponential curve because this is a log linear curve. And we can extrapolate and see what polynomial we need to get a particular level of accuracy. Right? And this is how we can select the right polynomial order in each direction. We can do it differently for each direction in our mesh, get the right polynomial order in each direction, and that allows us to select the right polynomial in each direction. When we compare the homogeneous polynomial to having the right polynomial in each direction, what we get is a very fast decrease in degrees of freedom. I'm gonna skip this because I'm not gonna have time. Okay, I'm getting into the machine learning ideas. So one of the things we are doing these days is trying clustering, for example, to determine the viscous and turbulent region after this cylinder, and then by knowing where is this interface, we can throw here a high polynomial order, which is the zone of the action where there's turbulence going on and everything, and here there's nothing happening. And here we throw a very low polynomial order. And we can do that with clustering. We can do that by selecting the right variables, which is basically the strain rate and rotational rate tensors. We can get this interface which doesn't require any threshold or anything, right? It's just you throw two clusters and it returns these two regions. And hence we can change the polynomial order in these regions. We compare changing the polynomial to not changing it, and we see that we get the right results, of course with much fewer degrees of freedom. And this idea of clustering we're exploiting for a few other things. Right, let me move into another idea of using neural networks in this case. Right, we've talked about higher the methods, higher the polynomials, lower the polynomials. So there's a big advantage of using lower the polynomials, and is that because we have a very coarse mesh, very coarse polynomial, we can jump in time much faster than with a higher order polynomial. If we have a lot of accuracy, because of the CFL condition, we require a very small time step, right? So high polynomials require very small time steps. We can advance in time very slowly. With lower the polynomials, we can jump in time much faster, right? So this is of course obvious, and the idea is, okay, why don't we advance with a lower the polynomial? Of course the solutions are going to be not accurate at all and very accurate. Okay, so you pay the price of the time stepping. But the idea is, okay, why don't we run the lower the polynomial, and every so often, so every time step, for example, we correct the lower the polynomial such that we get the filtered solution of higher order. So the very accurate solution in higher order. So that's the idea. We have developed that for 1D burgers. That was an initial proof of concept, and we have now in review the three-dimensional Navier-Stokes with turbulence, and I'll show you some examples. But again, the idea is very simple. So you write the equations for the low order, you write the equations for the filter high order, and of course those will give you different results, because one is very accurate, the other one is not. And the idea is, okay, how about we write the low order, but we supplement the low order Navier-Stokes equation with a source term that will correct the low order such that we retrieve the higher order solution. Where is this magic source term coming from? Well, from a neural network, right? So the idea is we're going to train a neural network to get for us these forcings given some solution, some velocities in the flow field. So what I'm gonna go back to this Taylor-Green vortex, this evolving Taylor-Green vortex, and I'm gonna run a higher order solution P8 and a lower order solution P3, which have a distance in time of 3. So we can advance 3 times faster with the lower order solution than with the higher order. Now what we're gonna do, of course, if we have to run two polynomials all the time, there's no advantage whatsoever in doing that. I'm running twice computation, so there's no interest whatsoever. But what I'm going to do is I'm going to just train my lower order solution to get this corrected forcing for a short period of time, and then I'm going to let it keep correcting my solution for a while and see if I get advantage after the training phase. If I get some advantage, then I'm getting acceleration in my solution because I don't have to train and I'm getting a better solution. Right, so this is what we get. When I'm comparing my polynomial order 8 minus my polynomial order 3 without any corrections, I get this error. We're in 7, right? Here there's no neural network whatsoever. We get this curve here. This is the error curve. Now I'm to the P3, to the low order, I'm supplementing it with this neural network correction. And what I see is that the errors drop, right? Of course, the errors drop whilst I'm training. This is natural, right? I'm training. I need the higher the solution for this phase. But I stop training here, and what I see is that I keep correcting my solution for a while, right? And all this part here, which is more than the double of my training phase, all this is acceleration, right? Here I don't need the P8 anymore. I need it just to plot the error, but I don't need it anymore, right? This is already corrected. So, and if I only look at this, I see that in P3 plus neural network, I'm 12 times faster than the P8, right? Of course, there's an elephant in the room, right? The elephant in the room is, if I was getting a P8 solution, the error will be down here. I will have no error whatsoever. So I'm not really recovering P8. I'm recovering something else. So what we did is we run a range of polynomials from P3 to P6 plus our enhanced P3 solution. And what we see is that what we are getting is something that looks like P5, P6 solution, right? So we need P8 for a while, we stop the P8, and then we keep correcting, and what we are getting is a P6 solution. So we lose some accuracy, but we recover some accuracy, for a long time after the training. Which, when we compare the cost with the P6 solution, which is our effective accuracy, what we get is 4 to 5 times faster for this region, right? So we think this is a very preliminary result, but it looks quite promising in terms of computing turbulence flows, etc. Of course, the last thing that one wants to check is, so this is an evolving flow. So we have large structures, here they're very fine structures. So is it really the method working all the time, only for isotropic turbulence, only for transitional flows, etc.? So we check for different windows, training and stop training, and we always get advantage. Right? We always get advantage. It changes, sometimes more advantage, sometimes less advantage, but we are getting advantage for all the types of flows. So we are interested in this topic, I think. I don't think I have more time. Maybe I'll stop here. It's just 2 slides, right? So the last thing we are testing is, so we realize when we do P-multigrid, so this is to accelerate our simulations to the steady state, for example. This is a one-dimensional problem that when we use multigrid, you have to project the solution in a coarser mesh. Sometimes you don't project all the thing, but you use you have some parameters in the multigrid thing, right? And these parameters, when you run your solutions, sometimes depending on the parameters, it blows up or it doesn't blow up, right? So you have it's very sensitive to these parameters. So instead of doing it by hand, what we try is to use reinforcement learning to select for us all these parameters, right? So as you know, probably reinforcement learning is what's used to run games and to beat people at playing Go or to playing chess, etc. So when we do that, we couple this reinforcement learning to our easy problem. What we see is that at the beginning, it starts trying a lot of different parameters for the sweeps. So these are just parameters into the multigrid. But eventually it finds the right solution, which is down here, right? So this is the relaxation levels of this number and sweeps in this number. And what we want to do is, well, explore this a bit further and try more complex problems in terms of numerics, but where the reinforcement learning can take decisions instead of us, right? For these challenging problems. Right, so I'm coming to the end. So these are the conclusions. You can always go ahead and try our solver. It's free, you don't have to pay us anything. And it's better than Fluent, we think. And let us know if you try and it doesn't work. We always want to collaborate. And there is all this physics, there is all these ideas here. Of course, we're looking for docs and postdocs, so if somebody's interested. So if you like computers like Bill Gates or you like fluids, you're welcome to drop me an email. And that's it. Thank you very much.